Okay, I hope you can see my screen right now. So we are going to analyze trust example 3.1. This is part B. So I have actually discussed this trust part A, okay, in my previous video. So we are going to actually I divide this trust into three parts of analysis. Okay, first part of analysis I actually introduced in my previous video about how to label nodes, how to label element, how to put the arrow, how to put the coordinate, how to analyze degree of freedom for each node, and how to produce nodal displacement and nodal forces, because nodal displacement and nodal forces will be used in the stiffness equation to calculate unknown displacement and unknown reaction forces. That is part A. Okay, in part B we are going to establish element stiffness matrices. This one, part B, element stiffness matrices K1, K2, and K3. And then we will continue to establish structure stiffness matrix number 2. So this is part B. So for this session, I will focus on these two output. Okay, these two output. Okay, so before we move to the output or outcome for this session, okay, we look at back to the trust, to this trust. So this trust consists of four nodes. There are four nodes: node number 1, node number 2, node number 3, node number 4. So node is actually join. Node is actually labeled for join 1, 2, 3, and 4. We use numbering instead of using ABC. Okay, and then we after nodes we have to label element. Element consists of two nodes. So one element, for example, element number 1 joining node number 1 and node number 2. Element number 2 joining node number 1 and node number 1 and node number 3, and element number 3 joining node number 1 to node number 4. Element number 3. So element is just like member A, B, member B, C, member C, D. Okay. So like what I explained in my first video regarding stiffness method. So what we actually do is we subdividing the structure into element. We subdivided the structure into element because we want to establish structure stiffness matrix. Structure stiffness matrix. The word is structure. The structure stiffness matrix mean the truss stiffness matrix. And in order to do that, we have to establish element stiffness matrices first. In order to produce the stiffness matrix for the truss, we have to establish the stiffness matrix for each element. And when we combine the element stiffness matrices, stiffness matrix for the element, we will get the stiffness matrix for the truss. Okay, so we have three elements, we have four nodes, three element, four nodes. Okay, so beside nodes and element in the diagram, okay, we have to have the arrow as well. And the arrow must be put parallel to the member, to the element. This is the arrow, And the best thing is we can put arrow in any direction that we like, in any direction that we like. Okay, in any direction that we like. We can put in this direction, doesn't matter. Okay, but in this question, the arrow is given in the question. Normally, if the question is okay, the arrow is not given in the question, we have to put the arrow, and you can put the arrow in any direction. Okay, so we just need to follow the direction given in the diagram. Okay, the arrow. So we have arrow. Okay, okay. Number four. Beside arrow. Okay, we have actually five important things that we need to put in the diagram. We call this as free body diagram for the stiffness matrix method. Okay, so beside these three, we have to have the coordinate. Okay, it is coordinate. So all this I have explained in my previous video. This is just revised back a little bit. Okay, so I I want to now put the coordinate. So coordinate means we choose one as origin. So let's say we choose node number 4 as origin. So this will be 0, 0. So based on this origin, we can get the origin for the other join, the other join. So based on this node number 1, we will get 4, 0. Okay, so node number, sorry, this is 4, 3, not 4, 0. This is 4, 3. Okay, and then node number 3 is 0, 3. And we have node number 2 is 0, 7. 0, 7. And this is very, very important. We have to put the coordinate. We cannot analyze anything without coordinate. We cannot analyze anything without coordinate. And stiffness matrix method is actually the theory behind software. When we model any type of structure in the software, we have to have coordinate. Okay, we have to identify coordinates. So okay, we have put all the coordinates. Okay, we choose one as origin. We choose one as origin, and from the origin we label the other coordinates for each joint. Okay, and number five, most important part. Okay, is the degree of freedom. Degree of freedom. Okay, degree of freedom. Degree of freedom for trust. Okay, is this is a degree of freedom, 2 degree of freedom per nodes. 2 degree of freedom per nodes. So if we have 4 nodes like this, if we have 4 nodes like this, means that we have in total 8 degree of freedom. 8 degree of freedom, 2 at each node. 2 at each node. So we have to put at each node, we have to put X and Y degree of freedom. Okay, X and Y like this. 2 here, 2 here, another 2, and another 2. And we have to put the degree of freedom in this direction. We cannot simply change the direction. We have to follow this as the sign convention in stiffness method, okay, in X and Y component. But the most important part is we have to label this according to unconstrained and constrained system. Unconstrained and constrained system, and I have discussed about unconstrained and constrained system in detail in this video. Okay, in this video part A. Okay, that is why like 1 and 2 1 and 2 is located number as unconstrained degree of freedom system. And node number 2, node number 3, and node number 4 due to support. Support has no movement. Okay, at support there are unknown reaction. So there are 6 degree of freedom in constraint system. There are 6 degree of freedom in constraint system. We can label as 3 here. We can label 3, 4, 5, 6, 7, 8 like this. Or actually we can label 3 from here. 3, 4, 5, 6, 7, 8. Also can. Okay. If the numbering is not given, we have to number the degree of freedom in the diagram. Okay, now the degree of freedom is given, so we just need to follow, okay, the given degree of freedom. And this degree of freedom has been labeled according to unconstrained system, unconstrained and constrained system. And okay, I have actually discussed about this in my previous video. Okay, so to establish element stiffness matrices, the keyword is stiffness. The stiffness symbol is K. Okay, the stiffness symbol is K. So in stiffness method, we will establish all in matrix, stiffness in matrix, forces in matrix, displacement also in matrix. All must be written in matrix form. So stiffness in matrix, we call it as stiffness matrix. We call it as stiffness matrix. And element stiffness matrices refers to stiffness matrix for element, stiffness matrix for each member. Okay, so since there are three members, element number 1, element number 2, element number 3. So we have K1, K2, and K3 here. K1, K2, and K3. So we have to produce this K using formula. The formula is always given. The formula is in the textbook. The formula is given in appendix. Okay, the formula, this is the formula in the textbook. Okay, and again, I have actually discussed about this, about the element stiffness matrices in example 14.1, the video that I have made 2 days ago. Okay, example 14.1, I discussed about example given in the textbook, how we establish element stiffness matrix. Okay, so in this formula, this is for element stiffness matrix. Okay, element stiffness matrix. Okay, there is the label here. F refers to the near end, near, and F is actually refer to far end. So how we identify near and far? Actually by using the arrow. So the arrow actually, using the arrow, we can identify which node is the near end node, which node is the far end node. Okay, so we will start with element number 1. So in order to analyze element number 1, the best is we draw back the free body diagram of element. We just draw the free body diagram for element number 1 only. Okay, this is element 1. Okay, the element 1. Okay, element 1. Okay, in element number 1, this is node number 1, joining node number 1 and node number 2. This is element number 1. Arrow is like this, parallel with the member. And from the arrow, because the arrow is always going to the far end, always going to the far end, so this will become far, this will become near. Okay, always the arrow is moving towards far end. The arrow is moving towards far end, so 2 will become near, 2 will become far, 2 will become far, and 1 become near. Okay, that is why the arrow is very, very important. Okay, we have near and far. We identify 1 as near, and we identify 2 as far from the arrow. Okay, so at node number 1, the degree of freedom is 1, 2, and at node number 2, the degree of freedom is 3, 4. 3, 4. 1, 2, 3, 4. And the coordinate is 4, 3. Is it 4, 3? Yes, 4, 3 and 0, 7. The coordinate is 0, 7. And the length, we have to calculate the length, of course, the length, because we need to divide by length here. So we calculate the length, and the length is 5.657. 5.657. Okay, so we have to calculate lambda x and lambda y, and lambda is also known as C. So maybe in other textbook, you will find lambda as Cx and Cy. Lambda as Cx and Cy. In past year exam paper as well. Past year exam papers, you may also find lambda as C. You can also write the symbol C to replace lambda. Okay. So how to analyze this? Okay, the simplest way is just focus on this and this. Okay, means that if lambda x is to be determined, focus on coordinate x, far minus near. It is far minus near. This is for far, this is for near. Okay, for lambda x, focus on x coordinate, it is 0 divided by 4 because it is far minus near. Okay, so we get 0.7071 negative. And for lambda y, focus on the y coordinate for near and far end. nodes. Okay, so for coordinate y, far is 7. Far is 7. Okay, this is far. Near is 3. Okay, this is near. So we get lambda y equal to 0.7071. Equal to 0.7071. Okay, 7071. Okay. So from this, we just need to substitute into the formula. We just need to substitute into the formula. So this is for K1. Okay, the formula is AE over L. This is L. Okay, this is L, AE over L. AE over L. So we just need to substitute the lambda x, lambda y into the formula and we get this. Okay, we get this. Okay, and then what we need to do is we have to simplify because we have to have AE as constant variable, constant. Okay, AE is constant. Length is not constant. That's why we have to just have the stiffness matrix in AE form like this. Okay, so we have AE times, okay, 0.0018, okay, like this, all this. Okay, they are 4 by 4 matrix. They are 4 by 4 matrix because the matrix, the size will be depending on the number of degree of freedom. And degree of freedom, there are two at near end, another two at far end. So that is why we get 4 by 4 matrix. And okay, this one is not completed. This one is not completed because the most important thing here is the degree of freedom label. Means that we have to label degree of freedom. We have to label degree of freedom. Okay, in this stiffness matrix for element, we have to remember that the first two belong to near end. The last two belong to far end. Okay, like this. The first two belong to near end. The last two belong to far end. So we have to replace this with the position, with the degree of freedom position. Near XY, far XY. So we have to label near XY, far XY in this matrix. 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's very, very important. Okay, so please try to understand this first before we move to element number 2. Okay, so we have to label. We have to label. So we have to repeat the same process for element number 2 and element number 3. The same process. The same process. Okay, so for element number 2, we move to element number 2 now. Element number 2, the length is 4 meter. For element number 2, the length is 4 meter. The length for element number 2 is 4 meter. Okay, the length is 4 meter. Okay, so in order to analyze element number 2, again, we do the same like what we have. Okay. Okay, now can you listen? Okay. Okay. Kena already listen. Okay, so we move to element number two. Element number two, so we just take out element number two. Okay, element number two. So we draw separately. We draw separately like what I am doing right now. So element number two consists of element two nodes. It is joining node number three and node number one. Okay, the arrow is going to the left direction. So from this we know that 3 is far, 1 is near. 3 is far, 1 is near. Okay, so we continue to calculate lambda x and lambda y. Lambda x is 0 minus, it is far minus near because this is far, this is near. So it is far minus near means 0 minus 4. 0 minus 4, we get negative 1. Okay, negative 1. And for lambda y, it is 3 minus 3 divided by 4, it is 0. Basically, if it is vertical, it is a horizontal member. Okay, we will find that the stiffness matrix that we get has have many zero value like this. Same goes to vertical member. Okay, then so we transfer into the formula, we get AE divided by 4, AE over L. So negative 1, negative 1 squared, we get 1. Okay, and then we get 0 because CX, CY. And then negative CX square. Negative CX square means CX square, then only put negative. So that's why we get this as negative 1 and this is 1. Okay, so complete this. We complete this and we divide by 4. We divide by 4, we get 0.25. We get 0.25 like this, 4 by 4 matrix for element number 2. And most important thing is, most important thing is the label. Most important thing is the label. The label is, we label start from near. We label start from near. Near is 1, 2, far is 5, 6. So it is 1, 2, 5, 6. 1, 2, 5, 6. 1, 2, 5, 6. It is 1, 2, 5, 6. 1, 2, 5, 6. The label of degree of freedom is very, very important. If you label it incorrectly, so the stiffness matrix for the truss, okay, will be wrong. So this is how we analyze element stiffness matrix. Okay, we move to element number 3. For element number 3, it is 3, 4. Length is 5. Element number 3, length is 5. Element number 3, length is 5. This is element number 3 like this. Okay, like this element number 3. So, bukan. Element number 3 are like this. Like this. This is element number 3. Again, this is node number 1. Node number 4. Arrow. Okay, coordinate here is 4, 3. This is 0, 0. Okay, length is 5 meter. Length is 5 meter. Degree of freedom. Degree of freedom. Degree of freedom. Okay, this is 1278. 1278. 1278. Okay, apa lagi? Oh, coordinate dah. Coordinate dah. Origin, coordinate dah. DOF dah. Arrow pun dah. Okay. So it is AE over L. So this one is not completed yet. So I don't change the value yet. That is why I copy from the upper step. Okay, so it is AE over 5. AE over 5. So we calculate lambda x, lambda y as usual. It is based on the coordinate. It is far minus near. So 0 minus 4. 0 minus 4 divided by 5, it is negative 0.8, negative 0.6. Negative 0.8, negative 0.6. So we get like this. Okay, negative, it is Cx square 0.864, Cx Cy 0.48, and we continue until we get all the value. So we divide by 5. So we change, we now change this one to the right value. Okay, so it is 0.64 divided by 0.64 divided by 5. It is 0.64 divided by 5. Okay, it is 0.125. Here, 128. Okay, next value is 0.48 divided by 5. It is 0.096. 0.096. Okay, so next value is negative 0.128. Next value negative 0.096. Okay, and line number 1 equal to row number 1 because the matrix is symmetry matrix, so it is 0.096. Okay, then we get 128. Then we get negative 0.096. Okay, 0.096. And for position, okay, this one, it is 0.36 divided by 5. 0.36 divided by 5. Okay, 0.072. 0.072. Okay, actually, if you study equal to these 4 value. Okay, so this is for trust only. So this is 0.128, 0. Okay, this one is 0.096. Okay, 0.096. So this one 0.096, and this is 0.072. Okay, and this, okay, this and this is also same value. Okay, but the difference is only due to the sign. So this one we get negative 0.096 and negative 0.072. Okay, so this is negative 0.096 and negative 0.0, negative 0.072. Wait. This is negative 0.072. Okay, so now we have completed the element stiffness matrix for element number 3. Element number 3, this is the matrix. This is the matrix. Okay, so as usual, we have to label. We have to label according to, okay, according to the diagram, near first, followed by far. Near first, followed by far. Okay, same goes to X and Y. X first, followed by Y. Means that X near XY, far XY. So from the arrow, from the diagram is 7, 8. So the label for this is 1, 2, 7, 8. 1, 2, 7, 8. Okay, 1278, 1278. Okay. Okay, now we have got all element stiffness matrices. Element stiffness matrices. Okay, here element number 1, 1, 2, 3, 4, the label. And then for element number 2, 1, 2, 5, 6, 1, 2, 5, 6. And for element number 3, 1, 2, 7, 8. 1, 2, 7, 8. Means that, okay, there are four nodes equal to 8 degree of freedom. So for the structure stiffness matrix, we will produce 8 by 8 matrix. 8 by 8 matrix. Actually, degree of freedom we label in the element stiffness matrices, okay, is to show the position. The position, okay, the position, and we will use this position to complete the 8 by 8 matrix for the structure stiffness matrix. Okay, so we have to, of course, we have to understand the metric characteristics. Okay, the metric characteristic number one, it is symmetry matrix. Metric is always symmetry. Metric is always symmetry. And then, okay, all this is the position. For example, if we want to calculate the value of 1, 1, 1, 1 position, it is just simple mathematics. 1, 1 position means we have to find 1, 1 from each K1, K2, K3. 1, 1. For example, I just wrote this just for the formatting 8 by 8. So I will replace with the value right now. Okay, for position 1, 1, for position 1, 1. Position 1, 1 is, okay, in K1 there is 1, 1. In K1 this is 1, 1. In K2 1, 1 is, in K2 1, 1 is 0.25. In K3 1, 1 is 0.128. So we have to total these three and we get the value at position 1, 1 for structure stiffness matrix. It is 0.128 plus 0.088. So we get 0.4. This is 0, 0.466. We have to do it one by one from 1, 1 position until 8, 8 position. From 1, 1 position until 8, 8 position. Okay, move to the next value is 1, 2. 1, 2 is 0.096. Okay, 1, 2 here is 0, negative 0.088. Okay, we get 0.872. 0.872. So the next value is 0.872. Okay, now we move to the next value. The next value is position 1, 3. Okay, the next value is position 1, 3. For position 1, 3, we get 1, 3 only from K1 because there is no 1, 3 in K2. There is no 1, 3 in K3. So we get 1, 3 value from K1. And 1, 3 value is negative 0. Negative 0.0 negative 0.088. Negative 0.088 is negative 0.088. Okay, continue with position 1, 4. Position 1, 4. Position 1, 4. 1, 4 also we can find in K1 and 1, 4 is 0.088. 0.088. Okay, it is just a simple mathematics. Okay, we just need to put the value, okay, put the value in the 8 by 8 matrix from that we get from K1, K2 and K3. Okay, we move to 1, 5 position. 1, 5 position, we get 1, 5 from K2. We get 1, 5 from K2, it is negative 0.25. It is negative 0.25. Okay, here is negative 0.25. 0.25. Now 1/6. 1/6 also we get from K2. 1/6 is equal to 0. So the value is 0. Okay, the value is 0. Okay, position 17. Position 17 we get from K3. 17 is equal to negative 0.128, negative 0.128, 17, and 18 is negative. 18 is negative 0.096. Negative 0.096. So find the value from K1, K2, and K3. Okay, and put the total in the structure stiffness matrix. So this one is 0.096 negative. So this one is negative 0.096. And again, this is symmetry matrix. Okay, symmetry matrix means line equal to row. Line equal to row. So it is 0.872 and negative 0.088 and then 0.088 and negative 0.25, 25 and 0 and okay, negative 0.128 and negative 0.096. Okay, so we have to replace all this. Okay, okay, this doesn't mean anything. Yeah, all this doesn't mean anything. It's just I get like this because I wrote any numbers to get the 8 by 8 matrix, the matrix form in this one note. It doesn't matter. Just change all this with value, the right value. So for position 2, so this will be position 2. This will be position 2. So we have to replace by the value we get from 2. 2 we can find in all K1, K2, and K3. 2. So where is 2? So this is 2, 0.088. It is 0.088. 2 in K2 is 0. 2 in K3 is 0.072 plus 0.072. So we get 0.16. So the value here is 0.16. 0.16. 0.16. Okay, continue. 2, 3. 2, 3. Where to get 2, 3? Where to get 2, 3? There is no 2, 3 in K2, K3. There is no 2, 3 in K2. 2, 3. Okay, we can get from K1. 2, 3 is, where is 2, 3? 2, 3, this is 2, 3. 2, 3 or 3, 2 is the same. 3, 2, 3 or 3, 2 is the same value. It is 0.088. 2, 3. Okay, it is 0.088. Same goes to this. And then we continue to find 2, 2, 4, 2, 4, 2, 5, 2, 6, and so on. Okay, so we have to do the same to get all the value. Okay, let's say I want to find the value. Okay, let's say, okay, I will replace this with position. Position. This is position. Okay, for if it is position, this is 2. Just now 2, 3. This is 2, 4. This is 2, 4. This is for position. This is position. Okay, so this is position 2, 4. This is position 2, 5. Okay, this is position 2, 5. So, okay, let's say I want to find what is the value for position 2, 5. What is the value for position 2, 5? Okay, let's find 2, 5 in K3. we don't have 2, 5 in K3. In K2, 2, 5. So we have 2, 5 here. 2, 5 is equal to 0. 2, 5 is equal to 0. So in the matrix, in the structure stiffness matrix, 2, 5 is equal to 0 value. 2, 5 is equal to 0 value. Okay, what about the value for 3, 5? Let's see. Okay, this is 3, 5. 3, 5. So what is the value for 3, 5? Okay, my question, what is the value for 3, 5? What is the value for 3, 5? What is the value for 3, 5? 2, 4, 2, 4 is negative 0.088. Okay, this one is negative 0.088. Okay, what is the value? Yes, 3, 5 value is equal to 0 because we cannot find 3, 5 in K1, in K2, in K3. Okay, when we cannot find the value in the element stiffness matrices, we will put, okay, the value at position 3, 5 by 0. So it is 0. Okay, so we try to complete until line number 3. Okay, we continue. This is 2, 2, 3, 2, 2, 4, 2, 5, 2, 6. Okay, 2, 6. Let's find 2, 6. What is 2, 6? 2, 6. 2, 6 is 0. 2, 6 is 0. 2, 7. 2, 7. 2, 7 is negative 0.096. Okay, 2, 7. This is 2, 7, negative 0.09627 here. Okay, 2, 8. 2, 8, we only find 2, 8 in K3, 2, 8. Where is 2, 8? 2, 8 is negative 0.072. Okay, okay, 2, 8. This is 2, 8. Okay, 2, 8. Okay, we move to row number 3. We move to row number 3. Okay, we find 3, 3. So what is the value for 3, 3? What is the value for position 3, 3? Where is the value position 3, 3? 3, 3, what is the value? And we can only find 3, 3 in K1. Yes, it is 0.088. So it is 0.088. 3, 3 is 0.088. Okay, so we move to 3, 4. Position 3, 4, what is the value? Position 3, 4. 3, 4 is inside K1. 3, 4 is inside K1. 3, 4. What is the value for 3, 4? 3, 4. Negative 0.088. It is negative 0.088. Negative 0.088. Okay, 350 just now. 36. 36. What is 36? What is 36? Can we find 36 in K1, K2, and K3? 36. Okay, we don't find any 36 in K1, K2, and K3, so it is equal to 0. What about 37 and 38? 37 and 38. 37. 37 and 38 also 0. 37 and 38 also 0. 37 and 38 also 0. Okay, so we can complete the row number 3 as well. So we have 4, 0 value. Okay, so this one is negative 0.088. Okay, the rest is 0. 0, 0, 0. Okay. Okay, that is why whenever you want to start analysis, you have to make sure that in the diagram you have to put the coordinate, the arrow, and the label of degree of freedom. Okay, that is very important. Okay, can you want to continue? Okay, I replaced the wrong row. Okay, sorry. So it is 0, negative 0.096, 0.096, and negative negative 0.072. Okay. Okay, one more thing. In the structure stiffness matrix yang ni, we have to write in order. That's why we do like that just now. This is 1, 2, 3, 4, 5, 6. Sorry, 6, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so for the degree of freedom in the structure stiffness matrix, we must write in order. Okay, not like element stiffness matrices where we have to label according to near xy for xy. But in the structure stiffness matrix, we have to put it in order. 32. Okay, 32 is 0.088. 23 is 0.088. Okay, same. Okay, 24. 24 is negative 0.088. 42 is negative 0.088. Okay. Okay, this one. 34. 34 is negative 0.88. 43 also negative 0.088. So this one, okay, this is negative 0.088. So the rest is 0, 0, 0, 0. Okay. Okay. So when we move to 4, we do the same. 4, 4, 7, 4, 8 until the last value 8. Okay, 8. What is 8 value? 8 we can get from K2. 8 we can get from K3. 8 is from K3, and 8 is 0.072. 8 is 0.072. Okay, basically the most uh that is not complicated. It is just time consuming because you have to do it carefully. You have to do it carefully. You have to fill in all this, okay, all the matrix, okay, from all the matrix, all the structure stiffness matrix from the element stiffness matrices. Okay, so I want you to complete this. We have remaining how many? Okay, this, please replace all this. Okay, please replace all this with the value, with all the right value. Okay, all the right value as I mentioned. Yeah, this one doesn't mean anything. Yang number dalam ni tak ada meaning apa-apa pun. It is just for me to get the matrix 8 by 8 into this. Okay, so please continue to calculate the remaining value in the structure stiffness matrix, because after this in the next video part C, in video part C, I will continue to analyze the remaining. Okay, so we will continue to establish force displacement equation. Actually, force displacement equation is only Q is equal to KD, and Q is equal to KD I have described in the first video. Okay, about the nodal forces, about the nodal displacement, Okay, there are eight nodal displacement, there are eight nodal forces. We write in matrix form Q and D in matrix form, and after we get K 8 by 8, we will write all in matrix form. So the force displacement equation refers to Q is equal to KD written in matrix form. Okay, so that is the answer for question number 3. And then after that, so in the next session, in the next video session, I will cover 4, 5 and 6. 1 2 3 dah cover. Okay, 4, 5 and 6. 4, 5 and 6, because from the stiffness equation or from the force displacement equation, we will solve output number 1 is displacement. Displacement is the first output. That is why we label one from unconstrained system, because displacement will be the first output, because after we get displacement, we can calculate reaction by using the displacement that we calculate. Okay, we cannot calculate reaction if we don't have displacement. Displacement must be the first. Calculate displacement and then followed by reaction, and then from the displacement as well, we can calculate member forces, because this is truss. Truss has beside reaction has also member forces. We can calculate member forces using displacement as well. So for step number 4, actually step number 4 ni will be used, okay, will be used separately. 4 can be used to determine number 5. 4 can be used to determine number 6. Okay, and the discussion about this, okay, about how to solve unknown displacement, how to determine member forces. Okay, I will discuss in the next video. Maybe today or tomorrow. Okay. Okay, so that's all for this session. Thank you for joining, and thank you for participate. So I will give you the link after the live. Okay. So if you want to join live session, so you can subscribe lah. Okay. So thank you very much. We will meet again in the next session. Okay. Assalamualaikum warahmatullahi wabarakatuh.